Hello everyone, I'm Lorenzo Calogero, and in this video I will present you my main research achievements during my 3 years of PhD. So, I'm currently a PhD student from Politecnico di Torino within the EECE Doctoral School, and my area of research is automatic control and system theory. Specifically, my PhD focuses on advanced model predictive control strategies for real-time applications. And as for my main research topics, you will see all of them in the next slides where I will present my works. So let's start from my field of research. And so what is automatic control? So imagine, as you see from the figure here, that you have a physical system that we call plant, which can be whatever real hardware in practice. And the task of the control researcher is to design a suitable controller that provides the optimal control input to the system. So to make it follow a desired reference trajectory, while staying within its physical limits. Okay, so typically actuation limits or output and safety constraints. In my research, I focus on an advanced control strategy that is called Model Predictive Control, or MPC in short, which is able to predict the future behavior of the plant while respecting any input or output constraint on the system. This powerful strategy, however, requires the solution in real time of a complex nonlinear optimization problem that you see reported here in the equation, which typically is too hard to solve in real time. And this is a key open problem in the field of MPC. And so my research aims at solving this problem. And to this end, my first contribution consists in solving nonlinear MPC problems using the Koopman operator. So the Koopman operator is a mathematical tool that allows to transform nonlinear systems into linear ones just within a higher dimensional state space. And so we thought of extending this Koopman framework to optimization problems, so to transform nonlinear MPC problems into linear quadratic MPC within this Koopman space, as you see here in the slide, which can be solved much faster and, importantly, is real-time feasible. Moreover, this approach is very interesting because it allows to reformulate the problem in the format required by quantum annealers, which are quantum computers that can exceptionally reduce the computation time even further. To validate, to test our Koopman strategy, were carried out simulations and experimental validation on 2 real-world case studies, so mobile robot navigation in cluttered environments, of which you see a video on the right, and autonomous parallel parking. Through these tests, we have demonstrated that the Koopman MPC proficiently attains the control task with a remarkable 10-fold reduction in the execution time, as you can see from the figure in the bottom right. My second contribution instead brings the computation times to even lower values by proposing a circuital implementation of MPC. So instead of solving the optimization problem of MPC on a high-end digital hardware, we directly realized an analog circuit made with commercially available components, which directly provides the optimal control input of MPC to the system. Thus, computation times reach microseconds, okay, so more or less the latency of our analog components. And you see the full circuit here in the slide, which relies on a mathematical variant of MPC that is called explicit MPC, and you can also see the experimental validation on the control of buck converters, which has outclassed all the major traditional control methods for DC-DC converters. The third contribution instead is what we call the neural adaptive MPC strategy, in which we emulate the MPC control policy by means of neural networks, so dramatically reducing the computation time thanks to the static nature of neural networks. And in conjunction with it, we have adopted a meteoristic tuning strategy that adapts the emulated MPC controller so to obtain multiple conflicting control objectives at once. And our case study in this case is power management in fuel cell hybrid electric vehicles, and here again, neural adaptive MPC manages to outperform all the major state-of-the-art strategies in this field. So to conclude, in this video, I've shown you some of my contributions on the topic of reducing the computational burden of nonlinear MPC problems, achieving very promising results. And looking ahead to future research avenues, I plan to explore the direction of quantum MPC, which is, in my opinion, a very interesting and fascinating topic. Then proving theoretical guarantees for Koopman MPC, especially for what concerns the closed loop stability, and also extending these frameworks to adaptive economic MPC, which is a more or less rising topic in the field of multi-objective optimal control. And that's it. I hope you found my research work interesting, and I thank you very much for your attention.